Today to talk to you about something slightly nostalgic. Back in the late 80s, I took a course entitled Discrete Mathematics, Combinatorial Mathematics. I think it was Discrete and Combinatoric Mathematics by Ralph Grimaldi. And I took the course under a gentleman by the name of Dalton Tarwater, a very prolific textbook publisher, and he's a good teacher. I had him for this course, Discrete Math, had him for abstract algebra. And he really liked the textbooks produced by Ralph Grimaldi. The Discrete Math book was very well written, a very lucid exposition. And I just wanted to touch on a few points that reminded me of those days in that topic. By the way, folks, if you don't know, discrete math is more or less the mathematics of the integers. It's more or less the same thing as number theory, a little bit of logic in it. And the combinatorics, the combinatorics is literally the mathematics of counting the states a system can be in. Now, what reminded me of this is I saw around my 10th YouTube video that was trying to prove why 0 factorial was equal to 1. And like seriously, it's like a spate of these proofs for something like that. And it certainly, I guess, something like that needs to be proved, but there's just so many of them. But I guess that's just the nature of YouTube. But anyway, just briefly talk about why 0 factorial is true. 0 factorial equals 1 is true based on this factorial identity. Now, it's certainly true that n factorial is equal to n times the quantity n minus 1 factorial. If you have to put numbers into it, just think of 5 factorial. 5 factorial is equal to 5 times 4 factorial. So it's just kind of a recurrent sort of definition. Now, if you hold that to be true, 0 factorial equals 1 follows fairly immediately if you choose n equals 1. When you choose n equals 1, the left-hand side becomes 1, and the right-hand side becomes 1 times 0 factorial. And so there's no solution to that other than agreeing to the fact that 0 factorial is equal to 1. Now, some of this stuff in mathematics is settled by convention. It may be just convenient to set 0 factorial equals to 1. So you could go either way with this. The binomial theorem, big theorem in mathematics, would break or not be as easily formulated if 0 factorial was anything but 1. And I'm going to demonstrate that here. Also, a lot of the stuff in statistics, you know, the binomial distribution, anything that depends on the combination formula that I'm marking through right here, that's what they call the combination formula. It reads n choose r. N choose r means the number of selections of size r that you can select from a set of size n, where it's an unordered selection. All right, now you can just eyeball it right now. If r was equal to 0, you could see quickly how this formula would break, right? You'd be dividing by 0, right? And this nice formula was actually is a great counting tool. Wouldn't work if you didn't agree that 0 factorial is equal to 1. So it holds for two reasons. It holds true to form on this factorial notation, and it needs to be true here. Otherwise, we would have to come up with another formulation for this type of counting principle. Now, just to show you a little bit about how valuable this formula is and how much labor gets saved, I went ahead and tried to do the a plus b quantity raised to the 4th power by hand. And you can just see the onerous amount of work here that's required to do this. In other words, you have, I'm using the distributive property twice here at the beginning if you guys want to take a look. In other words, a plus b times something is a times the something plus b times the something. That's what this says right here. A plus b times something is a times the something plus b times the something. The something just happens to be a plus b cubed. All right, but now you see it folds back on itself. Now you can distribute a plus b inside of here. And y'all, hopefully this color coding works for you. Notice I had to resort to bracket notation here because it's slightly unreadable if you don't use brackets as another grouping symbol instead of the parentheses. And so anyway, hopefully that kind of makes it a little clearer, but it's still a murky, nasty, burdensome sort of tedious process. Now, I went on through, did everything, and it actually came out how it's supposed to come out. This reads a to the 4th. That means 1 occurrence of a to the 4th. 4 occurrences of a b cubed, 6 occurrences of a squared b squared, 4 occurrences of a b cubed, and finally 1 occurrence of b to the 4th. And the reason why that obviously this is the only law you're really using here to do this is just the distributive property of mathematics. And what does it mean for something to be an exponent? After that, you're literally counting the occurrence of symbols. So this is a combinatorics exercise just as much, if not more, than it is anything to do with math, you know. Now, just a little bit more commentary here. Notice that you have 1 plus 4 plus 6 plus 4 plus 1. Well, that adds up to 16, which is a power of 2, which is what you would get if you let A equals B equals 1. And I remember that from Dr. Grimaldi's book, and I remember Dr. Tarwater talked about that, you know, but that says the sum of all these binomial coefficients is 2 to the power of the exponent. Okay, 2 to the 4th is 16. 1 plus 4 plus 6 plus 4 plus 1 adds up to 16. Now, just a little bit more and I'll be done with you guys. This literally says you could choose the way, when all this is said and done, there was 4 times when you could pluck out an A and a B cubed. This right here says there were 6 times when you could take out an X squared and an A squared and a B squared. So you see how this is almost pure counting. Now, if I'd done this completely right, you would end up with all kinds of stuff. You'd have to collect like terms, and there's no way you're going to get it right the first time. I almost did it, but you may notice right here, I appealed to the truth that A plus B quantity squared is A squared plus 2AB plus B squared. And that's cheating as far as the spirit of what I'm trying to do here. Now, let's move on down here and let you look at this in a formulation that may be a little more related to what I've been trying to get across here. Okay, now, so you can see, folks, right here, in lieu of A to the 4th, I put this thing called 4 choose 0. Well, here, the definition 4 choose 0, you get 4 factorial over 4 factorial, and if 0 factorial was not 1, this would not equal to 1, which it has to be, as we know, we've demonstrated that there's a coefficient of 1 in front of the A to the 4th term. Now, as an exercise, a lot of you guys probably already know about this, but you can verify that 4 choose 1 is equal to 4. 4 choose 2 is actually 4 times 3 divided by 2 factorial, which is 12 over 2, which is the 6 you see here. And that's a shortcut way to do combinations. You don't have to go back and look at that formula. You just go out the number of places of your R, like 4 times 3, 2 places, and then divide by 2 factorial, you get 6. Notice you got the symmetry going on here, 1, 4, 6, 4, 1. All right, now, but as far as a description of what 4 choose 0 is, it's, I know this sounds a little hokey here, but there is only one way to not select any B variables, right? There's not any B variables right here, and there's only one way to do that, and that's when you have nothing but 4 A variables, right? So it actually has, it has sort of a linguistic ring to it. And in a similar fashion, it's the same for 4 choose 4. 4 choose 4 could be also thought of as how many ways can you select only 4 Bs. Now notice 4 choose 0 would also be an interpretation, because you could just say how many ways not to pick any A's. So you see, that's why the symmetry holds, and that's what makes this such a beautiful result. I hope you guys enjoyed this, and be talking to you soon.